Hey, what's up, guys? Yeah, so today let's talk about the second examples of non-affine scheme, which is a projective line. So this example is also interesting. So let me just quickly go through it. So in the previous example, we give the scheme with the non-affine scheme example of the double affine line with double origin. So let's recall. So you can take x1 to be the spectrum of a affine line using a small x1. And then you take u1 to be the x1 minus the 0 point. So it's a spectrum of k of x1, and since x1 can be non-zero, so you can take 1 over x1, right? It cannot be 0. Okay, so you can take x2 to be the spec of kx2, and then you take u2 to be x2 minus 0. So you get two affine scheme and their open subset. And in a double origin, right? So one example is a double origin. You're just in map, you identify u1 to u2, but just mapping x1 to x2. Okay. So as we said, that this space looks like this. So because you just identify this, so for a projective line, you identify u1 to u2, but with x1 goes to 1 over x2. Okay, you can think a little bit. This is exactly the same as the complex version of the topological space. One definition of the projective space. So let me just quickly recall, right? If you consider the CP1 is defined to be, you take the two complex coordinates, and you are saying that x1, y1 equivalent to lambda x, equivalent to x2, y2 if x2 equals to lambda x1, y2 to be lambda y1, and lambda for any lambda belongs to complex, and you need to minus 0, 0. Right? Otherwise, this is ill-defined. Okay, and you can use the subspace topology or the quotient topology to make the CP1 to be the so you can imagine, you can immediately see that if in the first patch, let's say the first patch is x1 equals to non-zero, then x1, x2 is equivalent to 1, x2, x1. And for x2 is non-zero, the x1, x2 is definitely equivalent to 1 x1 divided by x2. So you can see that these two are equivalent, right? If these two are equivalent, then you are just mapping this coordinate to 1 over this coordinate, right? So x2 divided by x1 become x1 divided by x2. So it's exactly the same. If you use this, then it's exactly the same as this first patch in the algebraic geometry, just corresponding to open set of this, and this patch is equivalent to open set of this. So this is exactly the same as topological space. The only difference is that when we talk about this structure, then the patch, sorry, the structure shift will also get merged or get gluing. Okay. Okay, and the resulting space is called projective line. Just so basically you are giving the x1 and x2, and you neglect the 0 points, and you identify this x1 to 1 over x1. Okay, so some people will draw like this. If you see the Vacal textbook, and draw like this. So this is x1, this is x2. So this is x1, right? It missed 1 point. This guy also missed 1 point, right? Because there's a 1 point that's not gluing. Okay, and okay. So as we prove that in a double origin, as we prove that you take the global section, become isomorphic to the original K of x. And then we use this to prove that the double origin is not affine, because the maximum ideal is bijective to the point, right? So in this case, that we can also do this. Okay, and it's very simple that the proof is almost the same as the Liouville theorem in a complex analysis, but very simple. So right, if you take f, right, b belongs to k of x, let's say k of x1, and let's say, so you get f of x1, right? Let's say on u1. Okay, so x1 should not be 0, right? And now you're doing a gluing, right? So let's say you take another g of x2, and then let's say g of x2 on u2, so x2 should not be 0, and then they should be the same, right? So if x1 equals to g of 1 over x1, because x2 grew into 1 over x1, for x1 is now 0. So this is a condition that we hope to solve. And it's obviously too easy to see that this is impossible, right? Because unless f and g are constant, right? Because if fx1 is x1, then x1 cannot be 1 over x1. This cannot be true for arbitrary x1 non-zero. Let's say k is algebraic close. Yeah. So in this case, that you can show that the set of f is isomorphic to k, the field itself. Okay, so now we get a contradiction, right? Because the OX, if the this is the same as Louvenier theorem. Louvenier theorem says that the complex the only in bounding entire function on complex domain is constant, right? This is exactly the same as this. It's almost the same. Okay, so this will give you a contradiction, right? Because if the global section is isomorphic to field, then the spec of k will be a point, right? It will just be a point. It should be a single point, right? Because k is a field, so the spectrons, right? But this cannot be isomorphic to the pk1, a finite, because a finite has many points. Definitely should not have only one point, right? If you choose k to be algebraic close. Okay, so cannot be this. Okay, so which proof that the pk1 is not affine? At least for at least for k is algebraic close. Okay, and I think one can. I think, and by the way, and one can also show that this is true for general ring. Yeah, so let me just write down the argument. Okay, so one easy way to you can check that if you take the general ring, you can also prove that this is isomorphic to R, right? So if you take R to be arbitrary commutative ring with identity or a general ring, you can also prove as a skin, right? And so the question is that how can one one can show that R cannot be isomorphic to the projective plane respect to R. Okay, the reason is that there's an idea called respect R. Respect R cannot be isomorphic to the P and R. Okay, as a space. The reason is that there's an idea called dimensional theory. There's an idea called dimensional theory. Okay, so in a dimensional theory, that one can define a dimension of the ring. Okay, so in dimensional ring that or in the topological space, a dimensional ring will correspond to the dimension of the topological space by using the closed set at the trend line, then the ideal correspondence. And one can show that the dimension of R is less than dimension of R of X, also less than dimension of P and R. Okay. So yeah, if you use the dimensional theory, then you can prove they are exactly different. Okay. Simply speaking, is that if dimension R is D, then the dimension of P and R will be D plus N. Okay. So this is the same as dimension of R of X1. So dimension of this will be just the transcendental degree of this ring, right? So you basically get n of n, so D plus N. Then these two will not be different unless n equals 0. Okay, so this is the general strategy. This is the same as the same strategy that we proved that double origin is not affine. But in this case, that very simple, that we just get k, right? So k cannot be, at least for algebra close, this proof is very straightforward. Okay, see you guys in the next videos.